Hello everyone, my name is Gian-Marco Rignanese. I'm from the Université catholique de Louvain in Belgium. Today I'm going to discuss about the OPTIMADE REST API for querying materials databases. I will focus on the challenges that were faced and the opportunities that it offers. In materials science, high-throughput approaches have generated large amounts of data. These are typically stored in ever-growing databases, be it with computed or experimentally measured properties, publicly accessible or commercially sold. The explosion of data available opens new opportunities for concurrent materials design, such as using machine learning. Indeed, the databases can be queried online with an application programming interface, an API. It is often beneficial to have access to information from multiple databases. Indeed, they may cover different material families and properties. I will come back to that later in this talk. However, retrieving data from multiple databases is difficult as each database has a different API. Typically, to retrieve information about materials from a database, the user submits a request, a query to that database. This is typically done through a URL. Here, you can see the URLs that need to be entered for three different databases: COD, the Materials Project, and AFlow for querying about silicon dioxide. The three queries vary in format and in the strategy behind the specification of the number of elements and species. The wide range of query formats significantly complicates access to all available data for silicon dioxide. In fact, the subtle distinction between different requests, different for each database, requires the user to become expert in many different APIs. For instance, in order to prepare the queries for silicon dioxide, I had to discuss at length with some of the developers of the databases. And contrarily to what you might think, I'm clearly not the only one, as illustrated by the discussion that can be found on the forums of those databases. Now, not only the queries are different, but the responses as well. For instance, it can be a formatted HTML file by default, like for COD, as shown here. This may be very convenient for a human being, but clearly not for a Python script. Most often, though, the databases provide a way to obtain the response in JSON format, be it through the addition of some query parameter, or even by default, like here, or here. It should also be noted that, depending on the way the query is written, the response returned can be very different. Let us again take the example of silicon dioxide. The first query here requires the elements to be listed in alphabetical order and includes the one after element symbols so that SiO2 becomes O2Si1. This query only returns entries where the number of formula units of SiO2 in the unit cell is 1. The second query is in fact needed to obtain all entries with the SiO2 formula. The example illustrated in the slide focuses on just AFlow, but similar subtle things happen for each database, and being aware of all tricks is a real challenge. When we look at the JSON response from the different databases, they are clearly not structured in the same way. In the end, however, all responses contain a list of entries corresponding to materials. But each of these entries are again very different from one database to another. For all these reasons, the developers of various databases gathered in several occasions for a series of workshops entitled Open Databases Integration for Materials Design, hence the acronym OPTIMADE. These were held at the Lawrence Center in Leiden in the Netherlands in October 2016, at the SECAM in Lausanne, Switzerland in June 2018 and also in June 2019. The participants developed the OPTIMADE API. The OPTIMADE API provides a holistic tool to access information from any compatible materials database. The same query can be used, and the response format will be the same. Each database provider will publish a base URL that serves the OPTIMADE API, for example, http://example.com/optimate. The exemplar case of silicon dioxide is accessed through the query reported in this slide. There are actually some possible variants of it, but I'm not going to go into the details here. I just would like to highlight some important points. Therefore, I will comment a few sentences extracted from the specification. First of all, the OPTIMADE API builds on top of the JSON API, and JSON is the default format for the response. The specification covers what the response must and may contain. For instance, as we will see later, it may include links to other resources. The client may provide a set of URL query parameters in order to alter the response and provide usage information. While these URL query parameters are optional for clients, OPTIMADE API implementers must accept and handle them. To adhere to the requirement, query parameters that are not standardized by the OPTIMADE specification have been given names that comprise at least 2 words separated by an underscore. This makes it very easy to define identifiers that are specific to a provider by assigning each of them a prefix, as you can see in the slide. A new user can discover them quite easily as well. There is a list of OPTIMADE providers which keeps track of all reserved database-specific prefixes. It also includes the URLs to the index databases of all OPTIMADE database providers that participate in the OPTIMADE network. The list of providers is published in the form of a statically hosted OPTIMADE index metadatabase, both in human-readable format and in machine-readable JSON format. We now have a bunch of implementation of the OPTIMADE API at different stages. Some are already working with all the data of their provider. Some are working with a limited set of the data of their provider. Some are still being finalized. By the end of the month, I'm confident that we will have 10 working implementation. As I'm recording this video, I'm aware of 5 implementation with an info page. In alphabetical order, we have first COD, which you see here, and which is an open database with experimental results. The Materials Cloud, the Materials Project, and Nomad, which are all well-known large open databases with theoretical results. But there is also ODBX, which is a smaller open database from a group in the UK. As I had mentioned previously, a given provider can expose information on other OPTIMADE API implementations that are related to it through the links endpoint. This is the case here for the Materials Cloud, where links are provided to a series of connected databases. Thanks to all this, and thanks to shared tools, about which I will say a word later on, some providers have developed an app page where you can enter an OPTIMADE query to search their database. That is the case of the Materials Project, Nomad, and ODBX. As I mentioned earlier, some are still at the beta stage with only a limited set of their data, but this will evolve soon. More importantly, an app has been built that can be used to query different databases. Here, you can see a case where you can choose between the Materials Cloud and ODBX. For the Materials Cloud, you can pick among the different related databases. There is a simplified interface to enter your query, but it is obviously possible to enter a raw OPTIMADE query. And this tool also allows one to visualize the structure of the different results. A GitHub repository is available. The latest stable version of the specification is found in the master branch, while the latest development version is found in the develop branch. The GitHub repository also comprises two open libraries to help users of the OPTIMADE API. These include tools to aid the implementation of the API for materials databases, and the latter also contains tools to help a high-throughput script compose queries. The first, called OPTIMADE Filter, is a Perl library for the syntactical analysis of the OPTIMADE filter language. Apart from the construction of abstract syntax trees, the library is capable to translate simple filter strings to SQL queries. The second, called OPTIMADE Python Tools, is a Python package which contains some useful utilities for OPTIMADE API providers. The current functionalities include an extensible reference server implementation leveraging the modern Python tools Pydantic and Fast API. These tools are also used to generate a machine-readable Open API version of the OPTIMADE specification. It also includes a Python parser for the OPTIMADE filter language written in the Lark parsing library. And finally, filter transformers from the abstract syntax tree to queries to popular database backends. Currently, the supported backends are MongoDB via PyMongo, Django, and Elasticsearch. Based on all this, we may ask, where do we stand now and where should we go? Well, currently, the OPTIMADE API has been designed to address mainly the equilibrium properties of simple structures as obtained by DFT or experiments through COD. It would be nice if it could be extended for different kinds of properties such as responses, more complex structures such as surfaces, interfaces, or disordered systems, and other techniques such as embedded atom methods. In this framework, OPTIMADE will benefit from the support of the CCAM, which will hire a full-time postdoc for expanding the current developments to classical molecular dynamics or biosimulations. One important possible development for OPTIMADE would be addressing more experimental databases. Granta Design, the materials platform for data science, MPDS, with the Pauling files, and NIMS with AtomWorks have clearly shown interest in the OPTIMADE initiative and have actually participated to some of the workshops. In fact, as illustrated in this figure from a recent paper, most large experimental datasets like the ICSD, which typically contains hundred thousands of entries, are not diverse enough, as they contain only composition and structure of the materials. The diverse datasets, like Landolt and Bornstein or AtomWorks, contain hundreds to thousands of entries for different properties, so they are not large enough for training modern machine learning algorithm. In this figure, you can also see that the theoretical databases help going in the direction of increasing data diversity and size. The aim of that very paper was actually to report on progress towards a publicly open high-throughput experimental materials database, HTEM. At the moment of the publication, the HTEM database contained 140,000 sample entries. 100,000 of those were characterized by structural properties, 80,000 of those had synthetic information, 70,000 of those had chemical information, and for 50,000 of those, the optoelectronic properties were given. Those were inorganic thin film materials grouped in more than 4,000 sample entries across more than 100 material systems, and more than half of these data are publicly available. However, as you can see, these were released with yet another API. Wouldn't it be nice if this database could be queried also with the OPTIMADE API? As can be seen in this figure that I already showed, most of the past scientific data are not accessible because they are buried in plot images in articles. Here, I would like to highlight the Starry Data Initiative by Yukari Katsura, in which they want to recover as many data as possible by plot digitization. This initiative involves a lot of human time, but they hope that in the future, every data in published papers become accessible in digital form. From their platform, one can search paper whose bibliographic information is already stored. Starry Data helps researchers to visualize the data. Line plots, heat maps, single and multiple scatter plots can be drawn. Mouse hovering shows the information about each data point. This is a really nice initiative, but guess what? It was released with yet another API. I think that by now you should be convinced about the interest of the OPTIMADE API. So I will stop here by thanking all the people who contributed to the development of this API and who are listed on this slide, and by thanking you for your attention.